In the last lecture, we discussed about the Minkowski inequality. So with the help of Minkowski inequality, we can show that LP mu is a non-linear space. A small exercise. Show that LP mu with LP norm is a normed linear space where this norm is equal to T mod f p d mu power 1 by p. Okay, 1 less than p less than infinity. Okay, so now we'll discuss the completeness of LP mu. First of all, I will recall a result from function analysis. Recall a non-linear space, X is complete if and only if every absolutely summable sequence in X is summable. Okay, now we'll discuss the completeness of LP mu. Completeness of LP mu. The form of theorem. Let Xm be a measurable space and mu be a positive measure on M. Then LP mu with this norm, above norm, is a Banach space. That is a complete norm, a complete non-linear space. And also L infinity mu is a Banach space under the norm essential sup norm, essential supremum norm for p equal to infinity, for essential sup norm of f, essential sup norm of f. So we will discuss proof now. As I have given in exercise, so we know that LP mu is a normed linear space. Prove it and try it. Exercise. Simple exercise. Okay. we need to show that LP is complete. We need to show that LP is complete. Suppose we show that suppose 1 is less than equal to P less than infinity, and let Fn n from 1 to infinity be a Cauchy sequence in LP mu. Then there exists a subsequence. Then there exists a subsequence Fni of Fn such that norm of LP norm of Fni plus 1 is Fni is less than 1 by 2i, I equal to 1 to so on. Let Gk summation I from 1 to infinity, Gk means I from 1 to k, modulus of f, and take sum this sum of f modulus of Fni plus 1 minus F1i. We take a sum from 1 to I from 1 to k, and take and G equal to I from 1 to infinity mod Fni plus 1 minus Fni. Okay, and this you can see here, limit k tending to infinity Gk. Okay, then we can calculate LP norm of Gk. This will be equal to integral over x by definition of LP norm Gk power P d mu power 1 by P. Putting the value of Gk, what you get? Integral over x summation Gk I from 1 to k, correct, modulus of Fni plus 1 minus Fni power P d mu power 1 by P. This you have, correct. So using Minkowski inequality, we get norm of Gk. This is less than equal to integral sum equal to sum over integrals. What you get? Summation I from 1 to k, I from 1 to k, norm of Fni plus 1 minus Fni s. Okay, and you know from this Fni norm of Fn LP norm of Fni plus 1 minus Fni is less than 1 to, okay, this is less than 1 by 2i. This is geometric series 2i, and this is less than 1 by summation I from 1 to k, 1 by 2k 2i, correct, and this value is equal to 1, and this is finite. This implies GK belongs to LP mu for LP mu for K equal to 1 to so on. Okay. Now we'll appeal to Fatou's lemma, a major theory. Now, why Fatou's lemma? Integral x gp d mu, this value equal to integral x limit k tending to infinity infimum gk p d mu, and now by Fatou's lemma you have limit k tending to infinity infimum over integral x gkp d mu, and this value this value is less than equal to 1. This implies LP norm of G is also less than equal to 1. It's fine. And what this implies, G also belongs to LP mu. So what you have? So Gx is finite almost everywhere on X, and so the series add f1x plus summation I from 1 to infinity fni plus 1 minus fni is absolutely convergent. Okay, as G belongs to LP mu, so Gx is finite almost everywhere on X. So you know the value of G and X, Gx. So from here, modulus of this is finite for this is absolutely convergent for almost every X belongs to X. Okay, put this equation as 1. Okay, correct. Let fx be the limit of series 1 for all those values of x, for those x belongs to X for which the series 1 converges, and let fx equal to 0 for those values for those values x belongs to X for which series 1 does not converge. Then what we see is f is defined on whole of X. Then f is defined on whole of X. Now we shall show that f belongs to LP mu and Fn converges to f in LP as n tends to infinity. Okay, so what do we see here? We define fx value what you have taken here. Fx with the limit of the series 1 for all those x in x for which one equation series 1 the series 1 converges, and let fx equal 0 for those values x belongs to x for which one series 1 does not converge. So what you see, f is defined on whole of x. So what we have to prove now, we have to show that this limit function f is in LP mu and fn converges to f in LP norm as n tends to infinity. Clearly the sum of first k terms of the series 1 is, what do you say, series 1, put value here I equal 1, this will fn I 1 plus fn 2 minus fn 1 plus fn 3 minus fn 2. What do you see? All the terms with fn 1 will be cancelled by this fn 1, fn 2 will come cancelled by fn 2 and so on. Okay. What we are taking here? K. Means we are taking sum of first k terms of the series 1. F1 will be cancelled, F2 will be cancelled. We will left with only, this series is left with only F and K. That is, what you see, F and 1 plus summation I from 1 to K minus 1, F and I plus 1 minus F and I. This value will equal to F and K. Thus fx will be equal to limit I tend to infinity f and I x almost Ampere. Okay. Thus we see that f is pointwise limit of f and I. Okay, from here you have f is a pointwise limit of f and I, sequence f and I. Now choose epsilon greater than 0 since f and n from 1 to infinity is a Cauchy sequence what you get, there is some n in n such that what you have, such that what you have, norm of fn minus Fm P LP norm is less than epsilon. For all, you know the definition of Cauchy sequence. For all Nm greater than. Okay. So now we'll again apply Fatou's lemma. Using Fatou's lemma, we have f minus fm pth norm power p. We take power p integral over x. This will equal to f minus fm p d mu. So this you can write as limit x tending to infinity. Integral x limit I tending to infinity. Okay, f and I. Okay, you have taken f as pointwise limit of f and I minus fm p d mu, and this value equal to limit. Now we will apply Fatou's lemma. Limit I tending to infinity infimum over integral of x mod of f and I minus fm p d mu, and this value you can write like infimum I tending to infinity, limit I tending to infinity, limit infimum of this I tending to infinity. This value is nothing but f and I, LP norm of f and I minus fm. Okay, and this value you have less than epsilon. This is value is less than epsilon power p. Put this equation. What you get here? This LP norm of f minus fm is less than epsilon. So what do you get here? So this value is finite, this norm is finite. What it says? It means f minus fm belongs to LP mu. Okay. Since we know that, since you can write f equal to f minus fm and fm. Okay. Why now you can use Minkowski inequality. By using Minkowski inequality, what do you have here? LP norm of f will equal to LP norm of f minus fm plus fm, and this value is less than equal, you know, by Minkowski inequality, norm of LP norm of f minus fm plus p. Okay, and this value is finite, you know. Okay, correct. What from what you get here? From here, what you get? LP norm of f is finite, so it means f also belongs to LP mu. Okay. From equation 2, what we conclude? What we conclude with that fm converges to f in LP norm. Also from equation 2, you know the equation 2. This equation I have altered. This equation 2. What do you get? From question 2, we conclude that norm of Fm minus F goes to 0 as m tends to infinity. So this is what you have to prove. Okay, this proves that LP is complete for 1 less than p less than infinity. Thus LP mu is complete for 1 less than equal to p less than infinity. Now it remains the case of p equal to infinity. Now suppose p is infinity, takes value infinite. Let Fn be a Cauchy sequence in L infinity. Let AK, okay, consider set. Let AK equal to all those x in X such that modulus of Fkx is greater than equal to Fk, essential norm of Fk, and Bmn equal to all those x in X such that modulus of f and x minus f and x is greater than fn minus fn. For all what do you get here? For all k m n in n. Okay, so what you get here? Then mu of ak will be same as, will be what you have, this value will be 0 because Fk you have taken Cauchy sequence in alpha. Fk is elements of alpha into mu. That this means this value must be equal to, measure of this value should be equal to measure of all those x and x as for which mod Fkx is greater than the essential norm of Fk is 0. So this is 0. Similarly, this is also 0, equal to b mu of b m n. Okay, this is also true for all k m n in n, natural numbers. So let you take union of k m n belongs to n, ak union b m n. Okay. What this implies, mu of e is, this is this set has measure 0, this set has measure 0, and this is total union of sets are measure 0. So this is equal, measure of e is also 0. Okay. Okay. Clearly, Fn n from 1 to infinity converges to a bounded measurable function on complement of E, because you see here Fn is a Cauchy sequence and is bounded on complement of E. Okay, so on E define Fx equal to 0 on E, means I mean for all x belongs to E. Then what is here? Then F is defined on whole of x, and since F is bounded on x, so and measurable, and so F belongs to L infinity. Clearly by definition of essential sup norm of F n minus F, what you see here, this goes to 0 as n tends to infinity, and this proves that LP mu is a Bloch space, that is complete non-linear space. So some remarks are there. The norm on LP induces a metric D given y D of Fg is equal to norm of F minus G. Okay, so LP, you can say that LP mu is a metric space. Remark 2. So we have done shown that LP is a complete non-linear space for 1 less than p less than infinity. The question is, what happens when 0 less than p less than 1? In this case, LP is not a non-linear space. So, but even if it is not linear space, but it is still a metric space. Even more than that, it is a complete metric space. So what you see here, because when 0 less than p less than 1, the Minkowski inequality is reversed. That is, I mean, norm of Fg will be greater than equal to norm of Fp. So norm of P. So this Minkowski inequality is reversed. Though LP mu is not a non-linear space for 0 less than p less than 1, we have non-linear space for this. Still we have the following. I'll write in the form of theorem. If 0 is less than p less than 1, then LP mu is a complete metric space. With metric rho defined by rho of which we defined rho of fg equal to f minus this for all fg belongs to LP. This you have. So which is at least it is a complete metric space. So again I will say if somebody is interested in this generalization of these LP spaces or more about major function spaces, one can refer to all these spaces which are natural generalizations of LP spaces. One more, Laurent spaces, all these Laurent spaces. More generally, I will talk Banach function spaces. Lot of literature available on these type of spaces. Somebody is interested to explore these spaces of major functions. One can search for these spaces, and a lot of work is being done on this type of spaces. Many properties are being studied on all these spaces, Laurent spaces, Banach function spaces. Thank you.